the session. I'm gonna use Zoom, it's the easiest. Reem, can you please move away from my coffee? I don't want it to fall down. Okay, thank you so much. Okay, the content of today is the following. I want us to go back to data analysis for a bit. Maybe keep that until the end, I don't know. I also know that you don't have enough experience in data analysis, so I decided to include a data analysis discussion. It could be a problem, it could be anything, every live session. I'm sure it's gonna be beneficial for you. Okay, also we need to cover lab 1, and you will have your first graded assignment. Let me show you on Blackboard. So this is how your Blackboard is gonna look like. Can you see my screen? I assume you can you?
Yes.
All right, so this is your electricity and magnetism. Now you have a new section called Lab 1. On this page, I'm gonna share the recorded session along with any videos that we need, basically the video of the experiment, because I recorded the experiment myself. The lab report for you to fill in, because I did not give you any manual or lab reports yet, so I'm gonna give it weekly per chapter, so divided into chapters. And I don't know the results maybe, and so on and so forth. Under this one, this is an assignment. If you go under it, let me show you. You will see a deadline. It's next Tuesday before class time, and it's graded out of 100, so it's gonna be 1%, and you just submit your file. The file can be a document or a PDF, okay? And you click submit. Because I heard and I know from our previous assignments, they were not actually assignments, but you guys had difficulties to submit. You don't know where, you don't know how. Yes, and I have somebody who needs, can somebody help the student on WhatsApp? They need the link. Yes? Okay, let me do it myself. Give me a moment. I already sent the link to Fadi. Let me copy paste. Copy link. Oh, thank you so much. Okay. All right. So so now you have a place to submit, because I don't want you to submit whatever or to be lost, okay? And meanwhile, if you have any question or comment, please email me on the group or privately. Now let me put your names away, because I would love to keep track of some names. And if you guys have no internet difficulties, please put your cameras on. It's good for everyone. All right, so I'm gonna start with lab 1, tell you everything about it. It's a really simple lab. It's something you may be able to do in grade 9. The purpose of the lab is for you to get used to the equipment and to get used to the dynamics of the lab, something that we cannot do at the moment. But since we have an easy lab report, why not get used to the system, maybe submitting the assignment on time. Now let me fetch lab 1. I'm gonna start with the presentation. I'm gonna call it theoretical background, but if you really think about it, there's no theory really behind it. So okay, maybe make this a little bit smaller so I can keep the cameras on. All right, and move a bit so I can see your names. Lab 1, oscilloscope operations. You have 10 labs in total. This is the first one. The equipment that you need, I'm gonna show you on a recorded session, on a video, exactly the oscilloscope I used, the function generator I used, that is a little bit different than this one. The BNC cables are basically coaxial cables that I will use to connect the function generator to the oscilloscope. A question for Rudy. Rudy, do you see any measuring tool?
Yeah, I see the oscilloscope.
All right, Ryan, the oscilloscope, what does it measure?
You asking me?
Yes, Ryan.
The tension?
The tension, you mean the voltage or the potential difference? All right, so let's say potential difference. It's the best way to say it. Yes, the oscilloscope measures the potential difference only. It cannot measure the current, although I can deduce the current in some other cases, but it only measures the potential difference. It could be DC or AC. Maybe ask Tiana.
Yes.
Tiana, what is a function generator?
I don't know, is it
just say anything.
Provides the voltage?
Supplies the voltage. It's a generator. Can you tell me the different types of voltage it could give?
Direct and alternating.
It could be direct, it could be alternating. And for the different alternating, can you think of different types of signal that are alternating?
I know triangular and square.
Exactly, triangular, square. I can think of
one.
sinusoidal. All right, a function generator, you have many variables. What can you vary? Can you remember something about it?
Probably, I don't know, the period.
Maybe, yeah, the period, you can vary the period.
The amplitude.
The amplitude and the type of the signal. I don't know if you guys ever had the chance to play around with oscilloscopes and function generators. I know a lot of schools do not have this, and what I mean by play around is really take time to punch all the knobs. It's not only to observe the teacher doing the work. So maybe you didn't have the chance to do so, and maybe this is not super beneficial for us because nowadays we use sensors and the computer to do any measurement. So nobody uses oscilloscopes anymore unless you need to do something hardcore. But I wish when we go back to the lab, give you some time to play around with those. Yeah, and this is the BNC cable. I'm gonna ask somebody to try to speculate. Maybe Joe. Not here?
Yeah.
Joe.
Yes, yes.
Okay. Joe, my question for you is, I'm gonna connect the function generator to the oscilloscope using the BNC cable. I'm gonna pick a certain voltage, a certain signal, type of signal, certain frequency, certain amplitude, and I'm gonna observe the measurements here and measure again frequency, amplitude, period, and so on and so forth. I would see a slight difference between the measured value and the nominal value. I'm gonna call it nominal because it's written on the generator. Can you tell me why do I have a slight difference?
Difference in between graphics and
yeah, between the measurement on the oscilloscope and whatever you read on the function generator. Ludovic would love to help you. Ludovic, go ahead.
Yes, doctor. I guess because the BNC cables have a resistance that tends to zero. It's not exactly zero, but it tends to zero.
Okay, so Ludovic is trying to say that this is not an ideal case and we have some sources of errors. One of the errors is that the cable takes some energy out of my system. So I have some energy lost due to the fact that the resistance is not zero. This is one source of error. Anybody would like to speak up about another source of error?
Doctor, I don't want to speak about another source, but if the BNC cables were made of gold, ببطل عنا هذا.
Why do you think so? So you think gold has a smaller resistance than copper?
Yes.
Do you think the resistance of gold is zero?
No.
Not at all, which means we will always have some energy lost. But
Yes.
You have a point. Some material would have less energy loss, some material would have more energy loss. But anyway, it could be a source of error. Ali, would you like to add something?
I believe what Ryan was trying to say, I think it was Ryan, I'm not sure, I forgot who said it, but I think what he was trying to say is that the function generator shows an exact number, while the oscilloscope shows a graph. We could misread the graph or the exact value. I think that's what he was trying to say.
Okay, so this is another source of error, which means what I'm reading here is different than what I'm seeing here. But it's wrong to state this is exact because it has a limited precision. I can see 3 decimals. I would love to see maybe more. So this is also a limited precision. I will show you my function generator, and it has it was an analog function generator, not digital. So the smallest subdivision divided by 2 was not something to it was important actually. And I can see the limited precision of the measuring tool here because it's analog, so I need to count the number of divisions exactly like using a ruler. So these are three sources of errors. One, the cable, you lose some energy in the cable. Two, the function generator, whatever I'm reading on it has a limited precision. The oscilloscope measuring tool, limited precision as well. Okay? Thank you, Ali, for summarizing all of this. Now, all right, so this is something I want us to see. You have two different signals. I would want to move this a bit. Just random signals, just for the fun of checking some signals. How do we measure the peak-to-peak voltage? Maybe Ratib can help us.
We use the V times Y.
Okay, can you please explain?
Like then we multiply the number of divisions by the horizontal sensitivity.
Okay, so to find the peak-to-peak voltage, we must, by the way, peak-to-peak voltage is not the maximum voltage. It is the peak-to-peak. So from the maximum value to the minimum value. Usually, yeah, you can multiply it by 2 or you can simply measure it all. Some students actually divide it by 2 to get the maximum voltage. It doesn't matter. If they ever ask for peak-to-peak voltage, you do from the maximum point to the minimum point. You count the number of divisions and then you multiply by the vertical scale. We call it vertical sensitivity, or you try to look on your oscilloscope for something volts per division. Okay? Can you try, Ratib, to estimate, because I would love to move the signal right and left, can you try to estimate how many divisions is the peak-to-peak voltage? Estimate, or try your best. How many divisions?
2.4.
All right. So what is the smallest subdivision in this case?
0.2.
0.2 is the smallest subdivision. What is half of it?
0.1.
How many decimal is that?
1.
Only 1 decimal. So all your answers in divisions should be given up to 1 decimal, not more and not less. And we are not given the vertical scale in this case, which means we don't know the answer. Maybe I'm gonna ask Guisep. Hago, please mute yourself. Guisep, can you speak up? Okay, not here. Maybe ask Julnar. Not here, Michael.
Yes.
Okay, Ludovic would like to say something. Give me a moment, Michael. Yes, Ludovic.
Yes, I'm here.
Okay.
No, doctor. I was ready to answer if you would like to ask a question.
Okay,
I
I will get back to you. I'm just checking the attendance meanwhile. That's why I'm calling your names. Julnar, was it you speaking up?
Yes, I'm here.
Okay, so Michael, please wait a moment. Julnar, how do you measure the period? Do you have an idea? No? Maybe Michael can help out?
The horizontal sensitivity times the divisions.
Okay, how do you count the divisions? From which point to which point?
But no.
Michael?
Doctor, could you say it in French? The word
From the,
Yes, I can. Just let me know
Can you
which
repeat the
word.
scientific word?
Okay, so the question is, we need to find the period. Okay, the period of this signal. How do we measure the period of this signal? Michael said we take the horizontal sensitivity or the horizontal scale or anything that says milliseconds per division, and you multiply it by the number of divisions. My question is, how do you measure the number of divisions? From which point to which point?
from the beginning of the curve. From maximal to maximal. Yes.
Okay, so we can do from peak to
From
peak.
peak to a peak, or from
Trough to
the
trough.
X line.
or from the zero to the
from the center.
From the zero
Yes.
to the second zero. Maybe go back to Gulnar. Gulnar, how can you try
It has to be 1T.
Yes. Gulnar, can you estimate the period in this case? How about I take a pen and I draw it so we can keep it? So far you told me this is the peak-to-peak division to measure. Let me call it Y, PP standing for peak-to-peak. And for the period, you measure the distance that I'm gonna call X from peak to peak or from trough to trough, okay? Or from a zero, this zero, to the second zero, okay? I'm back to Ludovic because he was anxious to answer a question. Ludovic, what is X in this case?
3.2.
3.2. It's a little bit more.
3.3.
Yeah, but this is not. So basically, as you can see, we need to center our signal to be able to do some measurements. Before I move to the actual experiment, I need help with the frequency. Anybody would like to discuss how do we calculate the frequency that I'm gonna call?
Yeah, 1 over the period.
Okay.
Yes.
It's inverse of the period.
Okay. Ratib, would you help me out with the units?
Hertz.
Okay, so the frequency is gonna be in hertz. What about the period?
Seconds.
It has to be in seconds. If it's milliseconds, please make sure to convert. By the way, if I need to talk about significant figures and uncertainty, any measurement you do, please take the smallest subdivision divided by 2. This is like a ruler, like an analog measuring tool. You can tell how many decimals you have, and therefore can tell how many sig figs you can give. And the uncertainty is the smallest subdivision divided by 2. As you can see, there's nothing new in this lab. This is what? Grade 9 material. So let me now move to the lab recordings. These are the 3 YouTube videos I uploaded for you. It's the same lab. I just divided the different material used. Like in the first one, I explained the material used and how to do the connections and the functioning and the procedures, and maybe talk a little bit at the end about the sources of errors, but we already did that. Now let me fetch the documents because I don't want us to use more internet. So I have them saved anyway. So we're not gonna watch it all. I can send them to you, you watch it later, but maybe scroll down through most of it, okay? So, and maybe I'm gonna pause every now and then to explain something. All right. Hello there, this is the first lab for Physics 201L. The title of the lab is Oscilloscope Operations. Now, what are the equipment needed? You basically need an oscilloscope, 1. 2, you need a function generator, and 3, you need a BNC cable to be able to connect both. You know, this is your source of potential difference, and this is the measuring tool to be able to measure the potential difference over the voltage. Now the procedure. Let's play a little bit with our function generator. So what do we... All right, let me be quick. This is the amplitude knob. You can turn it to the right, fully clockwise or fully counterclockwise. You have the signal, sinusoidal, rectangular, triangular. Now the frequency is the tough one. You have different ranges. I don't know if you can see 1 kilo in here. So if I click on 1 kilo and put the knob on 0.5, I get 0.5 kilohertz. If I put it on 10K, and this is 0.5, I would read 5 kilohertz or whatever, 0.5 times 10K, all right? And this is the on-off button. This is all you need. This is the on-off button, all right? This is the different types of functions. So this is the sinusoidal function, the squared function, the triangular function. For the frequency knob, this is the frequency knob, but you need to multiply by the range. For example, if you need, I don't know, 500 hertz, you click on 100. I would like to ask Mark a question in here. Mark, are you with us? If not Mark, maybe Paul. Paul has internet.
Yes, yes, doctor.
Okay, Mark, is that you? Okay, so Mark, what is the error? Okay, I don't want this to happen. What is the error? What is the uncertainty on my frequency measurement?
0.1.
Okay, I don't know. The smallest subdivision in here is 0.1, right?
Yes.
Half of it is 0.05. Multiplied by the range, that could be 1K, I'm gonna have 0.05 times 1K. So you see? So for every range of frequency, I will have a different uncertainty. So I would want to use the smallest range possible, if I can, to have the lowest uncertainty possible. Keep that in mind. Also, when I go to the oscilloscope, it's the same thing. I will show you in a moment. Thank you, Mark. And you multiply by 0.5. Do you see this range? The knob here is on 0.5. So 0.5 multiplied by 100, you get 500 hertz. Let's say you want... Okay, I just did a mistake. 0.5 times 100 is 50 hertz. Okay, so I'm sorry for that mistake, but I believe you got what I mean. 1.5 kilohertz, you put the range on 1K, and you put this one on 1.5. You see, it's on 1.5 already. So 1.5 multiplied by 1K, you can have 1.5 kilohertz. Keep in mind that every time you do any measurement, you have to think about the smallest subdivision divided by 2. This is analog measuring tool. So we're measuring the frequency using this device, using an analog measuring tool. So the smallest subdivision divided by 2 multiplied by the range, you can have an idea of the uncertainty of your measurement. Also, you can vary the amplitude of your signal using the amplitude knob. So this is fully counterclockwise, will give you a very small amplitude. This is halfway clockwise. This is fully clockwise. It will give you a high amplitude, something like 25 volts or something close to it. Also, there's a secret. If you pull the amplitude knob out, this function generator will start functioning as a DC power supply. Okay, let's forget about the secret. I don't want to confuse you. So let's see what's remaining in this. So I'm just discussing frequency and different signals. So done with this one. The next one, maybe discussing the oscilloscope. In this video, you will be able to see the function generator along with the oscilloscope. Before we start doing some measurements, I'm gonna switch off, or maybe keep it on, because the only way for you to understand the functioning of the oscilloscope is to visualize something. I'm gonna put the power on. Wait a moment for the intensity of the signal to be... Some students freak out when they see an oscilloscope because it has so many knobs, it has 2 channels. So the best way to get really accustomed to this is to try them all, you know? Enough. I can see channel 1. This is channel 2, nothing on channel 2, because the cable is connected to channel 1, not channel 2. So I'm gonna go back to channel 1. I'm gonna put a sine function. You see the sine function is happening somewhere outside the scope of the graph. So maybe change the horizontal scale a bit, okay, to be able to view it. All right, so this is the scale. The signal will be actually not constant, but you have many ways to make it constant. But let's not waste our time now. Let's make sure the frequency is 500 hertz. And the signal is triangular, because again, it's easier to deal with triangulars. All right, usually I love using a triangular signal because it has a very sharp peak. So you can easily measure the period and the peak-to-peak voltage, you know. It's much easier. When you have a curve, you have to locate the midpoint. Your job is to measure the amplitude that is fully clockwise. This is a fully clockwise amplitude. You pick, so this is the vertical scale and this is the horizontal scale. This is called the vertical sensitivity and this is called the time base. I'm gonna pick a time base that would help my signal look a little bit constant. All right, so the signal was not as bad. This is what was showing on the camera of my phone. It was basically, yes, fluttering a bit, but not this much, and it was not moving right and left. So it was very easy to locate the peaks and to measure the distance between the peaks. So some scales will trigger some non-stable signal. So you pick a scale that will help you somehow, and this is all related to equipment, to voltage of the mains, to the cable, and so on and so forth. You can play a little bit with the trigger mode to make sure this is stable in a way. I know that the signal is blinking, but I can assure you it's not moving neither right, neither left, neither up, neither down. So my job is to measure the peak-to-peak voltage, and to be able to do so, I trust the graphical line in the middle, because I can see very small. Okay, what I mean by graphical line, there's a line in the middle that has the small subdivisions. You see it? Other lines, you basically see only the big division. You don't see the subdivisions. So the graphical line is the only line that would help me tell the subdivisions. So how about I use this knob to move my signal to the right, and use this knob to move my signal downwards. Okay, so now my signal is very well centered. I can easily take this measurement. All right, can you tell me how many division is this? Take a moment to think about it. Does it show? One. I cannot pause the video. 2, 3, 4, 5, 0.2, 0.4, 0.6. So this is 5.6 divisions. How many volts is that? The scale is 2 volts per division, so 5.6 times 2, you will have the peak-to-peak voltage. All right, I'm happy this is not too slow. I hope so. All right, now I explain how to do the period. So then you will have to change the amplitude from fully clockwise, and you can see on the screen how the amplitude is actually changing. So we were playing around, okay? We were playing around with the scale, 1 volt per division and 2 volts per division. Let me put this a little bit higher, okay? Yeah. You see the cable affects the measurement. Okay, this is so bad. شو اللي صار؟ بدك غير لا خلص هلا بعمل لهم trim لهو برجعوا. Okay, so apparently I did not trim the video, but it's okay. This shows some troubleshooting. So nothing happened. I just moved the cable and everything was good. بس لأنه خلصت الإكسبيرمنت غيرت الفريكونسي وما كنت عارفة أنا ما عم بيصور. وكنت ردها مثل ما كانت وهيدي كانت fully clockwise. All right, so now you're supposed to change the amplitude to halfway clockwise. So this is halfway clockwise, and you see that the signal is actually very small. Please do not take any measurement on this level. It's very important to remember that the uncertainty on your reading is the smallest subdivision divided by 2, multiplied by the scale. So you would rather use a... Listen, this is very important. You would rather use a small scale because the uncertainty is proportional to it. Scale, or in other words, a bigger signal and have a more precise measurement. So how about I change my scale to 1 volt per division? It's too big for me, so the signal is too big for the screen. So the smallest scale possible means the biggest signal possible. The smaller the scale, the biggest the signal. Let me move a little bit to the measurement of the period. Okay, I don't know if it shows. And then they ask you to go fully counterclockwise. That's and amplitude. Let me see period now. Change the frequency. I will keep my signal to triangular. And you see the big mess. So how about now we vary the horizontal scale to be able to view a nice signal. Your job is to measure the number of divisions between 2 peaks horizontally. So the bigger the better for the precision. I'm gonna position my signal on the horizontal graphical line because of the many subdivisions. It helps with precision. All right, so since you guys will have these videos on you, I urge you to watch them, to pause every time you want to rewatch again, and to ask questions if you want. Let me show you the lab report, because all this does not make sense if you don't know what is the lab report and how to fill it in. So the lab report should be here. So does it say reports? Okay, so these are all the reports together. Let me show you the first one for you to know what to expect. Okay. Yes. So I'm gonna send you lab 1 alone, then lab 2 alone. I don't want you to be overwhelmed, and maybe do some modifications. You will put your name. It's individual work, and the date is important. Individual work for many reasons, because it's easier for everyone. This is fully clockwise for the amplitude control, halfway clockwise, and then fully counterclockwise. I'm gonna give you the scales and the number of divisions, and you will calculate the peak-to-peak voltage, taking into account the significant figures. Then I'm gonna do the triangular wave, then the square wave, and you will see that maybe there is a difference or maybe not, okay? Then you have a frequency measurement. I will take each frequency, give you the scale and the number of division, and you calculate period frequency and the percentage error. What is a percentage error? This is very important. Let me write it in here. The percentage error is the difference between, usually we say the difference between the theoretical value, okay, theoretical value minus experimental value. Yeah. Yes.
Over the experimental.
Okay, so we find usually divided by the theoretical value times 100 to make it a percentage. And we take the absolute value because we don't care which is bigger. We care about how close they are to each other. All right, this is called percentage difference. Really, we don't call it percentage error. We'd rather call it percentage difference. Now, in my case, this is the nominal value. I can take it as my reference. And this is gonna be our measured value. So your job is to be able to compare them. So will I get 10 hertz on my oscilloscope? Maybe I will get 15 or 10.
Miss,
Yeah.
the frequency of function generator is bigger than the one we're going to get, right?
I don't know.
The theoretical is bigger.
I have no
It should be.
idea. I know I should have a certain difference. Bigger or smaller depends on how the different errors would affect my measurement. Maybe they will end up being the same. Remember, I'm rounding my values because I'm not allowed to give a very precise answer if my measurements are not precise. So maybe you will end up with 0% difference. Okay?
Okay, Miss.
All right. Then they want you to compare and comment. Comment means the sources of errors. Then they say, what is the role of the vertical position? What is the role of the X position control? Remember, the Y position is the one that helped me move the signal up and down to be able to center it. And the horizontal position control helped me to move the signal right and left to be able to center it and to be able to read it, you know, on the graphical line. Why should you maximize the size of the display? So you read this and you try to answer. So this is all the lab report. It takes a maximum of 20 minutes, knowing that I would be doing the measurements and I would be sharing the measurements with you. Make sure you type everything. You can send it as a document or as a PDF, okay? And I'm gonna correct it and grade you. Is that it for the lab? Maybe that's it for the lab. Yes, Ali?
But what does counterclockwise or like 50% counterclockwise
Okay, so
mean?
do you see the amplitude knob here?
Yes.
Okay, so I take the amplitude knob and I rotate it fully clockwise. Fully clockwise means highest amplitude possible. Fully counterclockwise means the lowest amplitude possible. Okay? So CCW is counterclockwise.
سيكون عندنا مثلا إذا if it's 100% counterclockwise لكن بتكون هالقد وإذا clockwise هالقد بتكون.
Yes, I remember some values. Fully clockwise was very close to 25 volts and fully counterclockwise was very close to 3 volts, 4 volts, I can't remember. like small voltage, like I need to zoom in to be able to see it. Zoom in for me means pick a scale that is very small to have a big signal, and therefore that's zooming in for me. Okay?
No.
Cool. All right. Shall we go back now to data analysis? There's a section. By the way, today you will not use anything from lab 0, but one idea, significant figures. I still remember we have a tiny section that we did not cover, the error on the slope. I still remember that we discussed how to find the straight line and how to understand I have more error in here on the slope than in here. But how do we find the error on the slope? Like if I find the slope doing linear regression, everybody I suppose did that. You did linear regression using Excel or your own calculator, right? Can I assume you know how to find the slope?
Yes.
Please speak up if you don't know how. Maybe I can prepare a video, another video to show you how I do it.
Can we share the answers?
Yes, how about you share your answer? What did you plot? Let me insert a text here. Yeah. What did you plot?
The slope is
Okay, you're supposed to plot y versus x. What was your
yes,
y-axis?
y-axis is u.
Okay, you've chosen the u to be your y-axis. Let me call it voltage. Okay, 1 second. Voltage. And what did you choose for x?
I.
Okay, the current. Okay, and then what the slope did you get?
1,787.
1,787. Did you change your current to amperes?
0.32.
0.32. Can I assume your current is in amperes or milliamperes?
Ohm.
Okay, so the slope is gonna be volts per amperes, which means ohms. I assume that you converted your current to amperes. If you did not,
Yes.
please do so. Yes, all right. And can I assume that the slope represents R or 1 over R?
1 over R times 1 over I.
Okay, so the slope represents R. So this is the actual R of my circuit. Do you agree?
Yes.
Anybody?
Yes.
Okay, anybody else did this calculation and they do not agree with these values? So I assume everybody agrees. Okay, let it be. Now the question is, what is the error on the slope? If you do the plot on Excel, you will see you have some scattering around the best fit. So definitely you have an error, and the error would help you round your value. Like if the error is 1 decimal, you round the slope to 1 decimal. If the error is no decimals, you round the slope to no decimals. Anybody? Okay, so Ratib is saying that the error is 0.068. Am I right? Did I read it well? 0.068. Let me open the chat. The chat should be here because I have Zoom open and okay. So she said, okay, this is the slope. Do you agree with the slope? We know, I mean the error. We know that the error should be one significant figure, right? So this has to be rounded. How do you round 0.068 to one significant figure?
7.
0.07, you mean?
0. Yes,
all right,
yes.
so Celine is asking, should we force the line to pass by the origin in Excel? No, Excel will give you the best fit, and Excel will give you the y-intercept and the slope. All right, and the y-intercept will not be 0. It's going to be very close to 0, meaning that you're close to the origin, but not exactly the origin. Ratib, please speak up. You have a question.
No.
Okay, you're fine? I don't
Yeah.
understand what you mean approximately 68 with conversion.
I thought that we should
Convert to milliamperes?
to ampere.
Okay, so your answer is 0.068 using milliamperes
Yes.
or amperes?
Amperes or milliamperes, because the 10 raised to the power of -3 would be eliminated from downwards and upwards.
Are you sure? Because the error has a unit. And I suppose if you change to milliamperes or amperes, the error would be different. I'm not sure I agree with you. Okay, now some students are wondering how we did the error, because I never had the chance to explain how we found the error. Ratib, would you want to explain how you did the error?
Yes. I first squared the current,
Okay,
and then we found delta, which is equals to n, the sum of current squared minus the sum of current raised to the power of 2.
okay, so let me help Ratib by showing you this video. I'm not gonna error on the slope. I'm not gonna play the video because I know you can play it on your own. Okay, where is it? This. Okay, I want to show the equation and go quickly, unless you want me to go slow. Okay, so basically this is the equation, this is the error on the slope. Don't forget to square root your answer. N is the number of points. N minus 2 is the number of points minus 2. Delta is given by this equation. Again, sigma xi squared, you take all the x's, you square each and you add them up. Sigma xi, all of it squared, you add all the x's, then you square the whole answer. What is E1? E1 is y minus y1, or bx1 plus a minus y1. B is the slope that you already get from the plot, okay? A is the y-intercept that you can get from the equation of the line. Y1 is what you can read in the table. So you find E for each set of coordinates, then you square each, then you find the sum. The video is very informative. I wrote A and B here and N here. You do the calculations for sigma EI squared because I already have it here. I already did the calculation for delta, plug everything in, okay? A lot of students do this work on a paper using a simple calculator. I like to do this on Excel because I do one calculation and I drag, okay? Because you know how, I don't know if you know how to use Excel to do the calculation, but you can watch the video to learn. And my Physics 306 students decided not to use this method. They decided to use the Linus method, okay? The Linus is a function on Excel. Think about it, maybe we can do that. I don't really care at the moment because you need to find the error on the slope maybe 3 times during the whole semester. So maybe keep the equation, it's okay. So Celine is saying, but if it doesn't pass by the origin, then the equation is y is equal, let me correct you, bx plus a, while our equation is in the form, which is okay, Celine. Don't forget that a, which is the slope in your case, is gonna be approximately the resistance, and the approximation due to the fact that b is not 0 is due to the sources of errors. So Celine is trying to be precise. Celine, don't kill yourself being precise. Let me tell you something. All the experiment is not precise. So if you end up with a slope that is not precise, you have to live with it because this is your setup, this is your procedure, and you cannot seek a better precision, and you have to accept it, all right? Yes, I don't know, I'm sure that I did not convince you. Celine, you need time to experiment with errors to be able to be convinced. I want you just to cherish the beauty of real measurements. What you learn in the course is the ideal case. And the ideal case is something that does not exist. You cannot see the ideal case in nature. You cannot see it in the lab. What you see in the lab is the real case. And trust me, nobody is going to teach you the real case. So when you see real measurements and a lot of errors, you freak out and you don't know how to behave. Trust me, this is the beauty of nature and you should accept it and know how to adapt in it, okay? That's why you would see in this lab a lot of questions around, like revolving around the sources of errors and what are the uncertainties and how to do the error analysis, because this is something you cannot learn in the course, okay? And it takes time, because I suppose you're 18 years old, maybe older, and you've been tricked for 18 years thinking the ideal case is what we need to trust, and thinking all these measurements are numbers, mathematical numbers, which is not the case, you know? So if you believe you're having difficulties grasping significant figures, accepting those errors and uncertainties and estimations, it's okay, you need time. And I totally respect this, okay? That's it for us. I know we did not finish everything because we don't have a limit. Let's keep on discussing things throughout the week. If you have any question, you let me know. Meanwhile, you have an assignment. Yes, it is due next Tuesday. Try to submit your work by the end of the week. Don't wait until the due date, okay? Because now maybe it's fresh in your head. Watch the videos well. I will upload everything tonight so you can start tomorrow morning. Let me know if you have questions. Anything else?
So questions in the lab. The last questions.
Yes. Yes, Joe.
Where we write?
Okay. Say it again. Where? Where do you find the documents?
Yes, yes.
Okay. So when you go to Blackboard, that is here, I'm gonna post everything related to Lab 1 under the folder Lab 1. So far, it's empty. So if you go to Lab 1, this is where you submit your final assignment, but you're gonna see the recorded session, the lab report, the videos. Maybe the videos, listen, the videos, I don't want to post them. Why? Because you have them in the PowerPoint. So on the last slide of the PowerPoint, you see the YouTube links.
Yes.
So these are the videos. I don't want to overwhelm, because for other classes, look at my other classes. They have like 1 million files. They have where to submit, the PowerPoint, 3 videos, 2 results, the recorded session, the lab report PDF, the lab report doc. So if I skip the videos and keep them under the PowerPoint, it will be more organized. For the results, maybe I can include the results inside the lab report. I don't know. Or maybe give you the results alone and the lab report alone. The recorded session, I need to put it anyway. It's gonna be a YouTube link. Okay?
About the answers, where we write the answers.
Okay, you open the lab report. It's gonna be empty, exactly like I showed you. Did I close the lab report? Maybe it's still here. This is what? The lab report. Okay, I'm gonna give you a lab report where you have only the measurements. So I'm gonna fill in the measurements for you. And like, for example, I would fill this in and this in, and you do this and this and this. Okay, so I will give you the measurements, maybe in red, and you continue filling in the table and answering the questions. In the documents, you type them. Nothing is handwritten, everything is typed. And then you save your document. But please send me only the lab reports. I mean, starting this point and ending this point, those 2 pages. Do not include other lab reports. Do not include the manual, because I will send you also 2 pages of manual, okay? That would summarize what we did. So you have a lot of references to keep. So you go to your course and you go under lab 1 and you will see everything needed. Okay?
Okay.
And if there's something not clear, just text me anytime you want. My email is always on high notification. Yes? Yes, Antonio?
How do we know the small subdivision?
From the videos. So the videos will show you the measuring tools, and I believe the videos were clear enough. Maybe not the first one, the second video or the third. You had something very similar to this one. So you can read the smallest subdivision divided by 2. Okay? On the video I sent you, wasn't it visible that the smallest subdivision is 0.2? I was counting 0.2, 0.4, 0.6, right? In case you missed it in the future, maybe just ask me.
Okay, thank you, Doctor.
All right. Thank you so much for this session. I enjoy Physics 201 a lot. Look at you involved. The attendance is high. You ask questions, you give answers. Other classes are not like this. I really enjoy your class. Thank you so much. I'm gonna stop recording. If you have any questions, stay behind. Yes, Rudy. Rudy is.
Thank you, Miss. Just want to say thank you.